Yeah, so it's 6:35, so let's start. So hello guys, this is Avinash and yeah, from Everything Metallurgy. So one more guy. So today, thanks for first of all, thanks for joining in us for this demo class. So this will be about 30 to 40 minutes where I'll be discussing about and also explaining about how this live session is going to be. Okay. So first thing I wanted to tell is this call, okay, is through Zoom. Like as you all know, you have joined through Zoom. This is only for the demo purpose. I'm just making it clear. We are having a virtual classroom for us, okay, which I'm not going to keep out. So this is not for the experience of how the session would be, but this is to tell you what will be the course. And yeah, obviously many people came to see how will be the teaching and what all. Okay, so let's get started. So today, briefly what we'll discuss is about phase diagrams. I hope everybody is able to see what I'm writing. Okay, so what is a phase diagram? So phase diagram tells us about the mapping between the temperatures and the composition usually. So this we are using the terms temperature and concentration because usually we are bothered about binary diagrams. Okay, and these are the two degree of freedom we use for uh, starting up. Okay, these two are the main degree of freedom which we use to draw a binary diagram. And one more thing that yeah, someone is texting, just a minute. Can't see your screen. Is the screen visible to everyone?
Yes, sir.
Yeah, cool, thank you. So yeah, so as I was telling, so we are discussing about phase diagrams, and we want to discuss what is a phase diagram firstly. So it's nothing but mapping between different degrees of freedom. So in our case, in binary phase diagrams, usually we want to draw between the temperature and compositions. Okay, so not only this, if at all you want to draw between temperature, composition and pressure, so you have to have three axes. Okay, so usually on paper you cannot draw the three axis diagrams, so we usually take the term pressure. Okay, usually take pressure to be constant and we draw. Okay, can somebody mute the microphone please? Yeah, so this is what a phase diagram is. Now this tells us about the relationship between this. Obviously the mapping is nothing but the graphs between temperature and composition. So this pressure, why we are taking it constant, is because we can't draw three axes on a plane of paper. So that's the reason why we take temperature and composition. So now there should be some deciding rule. Okay, there should be some deciding factor through which we can do this. So we use Gibbs phase rule for the same. Okay, we use Gibbs phase rule. Now what does this Gibbs phase rule tell us? So usually I think you all know this. F is equal to C minus P plus 2, where F is my degrees of freedom, C the number of components, P is the number of phases in the system, and obviously F is the number of degrees of freedom. Okay, so this is usually for any system. Okay, but here what we are doing for our easy purposes, what we are doing is we have removed the term pressure. I mean, we made that constant. So usually whatever you see is drawn at a constant pressure, or rather atmospheric pressure. So for that purpose, the same thing, the same Gibbs phase rule is turned out into this thing. Okay, so one degree of freedom has been subtracted. So That is what the reason is. Okay, so the normal Gibbs phase rule is converted into -1 by subtracting 1 degree of freedom, as we are ignoring the pressure term while considering our experiments. Okay, so this is the thing that about phase rule. Now, so as I started with the term Gibbs phase rule, we have just finished it. So what we are going to discuss today is about the binary system. So what is this binary system? So this is the most commonly used system, or this is the most commonly used diagram. Okay, so in order to tell us the relationship between two components. Okay,
Why temperature, sir?
someone was talking.
Why temperature actually, sir, neglected instead?
Oh,
Pressure is neglected instead of
yeah, actually, can I take all the questions at the end, because the session will be only
okay,
for 30 minutes.
okay, done.
Fine. Yeah, thank you.
Done.
So yeah, so where I'm yeah, the binary diagram. So binary diagram is usually telling us about the relationship or the mapping what we talked between two components. So I think you all know the iron carbon, or in between two phases. For example, if you take, we also have Fe3C. Okay, so likewise, so this is what binary system or binary phase diagrams explain us. Okay, so one thing I again explain is this. Okay, this is what is the binary system tells us, where we express the temperature on y-axis and the composition on x-axis, and usually we utilize the unit. We use the unit of, okay, percent weight or percent atom, or rather in the opposite way, however you want to call, weight percentages and atom percentages. So these are used as units for the composition axis. So everyone knows how to calculate the weight percentage. So the weight of some component by the total weight. Now, what is this atom percentage? So from the weight percentage, we can easily calculate our atom percentages. So how? So for example, if I'm considering a binary system of A and B, okay, if I consider a binary system of A and B, and I am calculating atom percentage of B, that will be equal to this thing, weight percentage of B divided by the atomic weight of B divided by the total, actually, that is nothing but the weight percentage of B by atomic weight of A plus percentage B divided by atomic weight of B. Yeah, obviously into 100 will become, if you want to calculate in percentages, otherwise this will be a fraction. Okay, so these are the units that we use for uh, the axis on the composition. Now we'll just discuss about the briefly about the types of these binary diagrams. So first diagram, that is the isomorphous system, isomorphous phase diagram. So what is this isomorphous phase diagram? So it tells us, okay, it tells us about a binary system, okay, where for example, if I take AB as my components, that means isomorphous tells us that there is 100% solubility, or we say solid solubility something. So that is denoting that B can go completely into my A, and A can also dissolve completely into my B. That's what solubility tells us about. Okay, so what is this isomorphous diagram look like? So this will be something like this to look like, and how this came, what are the derivations, and also if you also want the G versus X curves thermodynamics behind it, then we are going to discuss everything of that. Okay, so as I already said, this is the temperature, and this is, yeah, let's take B. So this will be pure B at 100 percentage B, and at 0% B it will be pure A. Okay, so if you see here the temperature, okay, these are the regions: liquid, solid, and liquid plus solid. Now here what I was talking about is that the solubility. So if you can see here, there is no barrier of how much B can go into A. Similarly on the other side, right? So if you see here, the 2 points are on the axis itself. That means that there is no barrier of how much B can dissolve into A or how much A can dissolve into B. This is what isomorphous diagram tells us about. And here we know that above a certain temperature we'll be getting a liquid, and similarly below some temperatures we'll be having our solid. So there will be a common position, okay, common position in the sense the intersection area. So in our graph, so if you see, this is a two-phase area. Okay, so yeah, obviously liquid is a phase and solid is a phase, so that is a two-phase area. So now what we are interested in is to calculate how much is a liquid present, how much is a solid present, because as there are two phases present here, we want to study about it. Now how to do it? So just to know that, we have some rules, just like to draw this how we have the phase rule and all, we have some more rules for this. So which is tie line rule, or simply tie line, and the other one is a lever rule. Okay, so these are the two rules, and I'll just briefly explain about what is what. So now first, if you see about the tie line, okay, so at certain temperature, for example, if I want to have a look at this temperature T1, okay, I'll just draw a line that is parallel to my x-axis. Okay, what I did is I drew a horizontal line that is parallel to my x-axis, and because of that, what happens, it is intersecting my diagram, my phase diagram, at 2 points, right? Okay, for example P and Q. Okay, so yeah, and one more thing is that the intersection where the liquid, the intersection of this two phase region and the liquid region, that is this line. Okay, this line, as you can see here, that is the intersection line between my two phase region and liquid, that is called liquidus. Similarly, I also have other line which is the interface between two phase and solid, that's this one. Okay, which is called as my solidus. Okay, so now if you see what the horizontal line is doing, it is cutting, it is intersecting my solidus and liquidus at two different points, that is P and Q. So these points have some significance. So now this P, wherever it is intersecting, if you just project onto my x-axis, it will give my fraction of liquid. Yeah, sorry, it gives us the percentage of B that is present in the liquid. Okay, similarly Q. Okay, so similarly Q, what does it do? It also gives me the same thing, the percentage of P in solid. So as it is intersecting the solid, so you can write the percentage of B in solid. Okay, so this is what it is. So if you see here, the composition of liquid and solid can be calculated. So what is the composition of liquid? So that, for example, if I have 40 here and 60 here, so I can say that 40% B is my composition of liquid and 60% B is the composition of solid. Okay, so these are the uh, compositions. So 40% B in the sense 60% of A. So just the other way, or for the other case. Okay, so this is the first one, tie line rule. Okay, in order to calculate uh, the compositions of solid and liquid, we use this. The next is lever rule. What is liver rule? So if I have an alloy, okay, so I have some alloy somewhere here, okay, for example 50% in my case, okay, I'm just assuming 50. So how much will be the fraction? Okay, as we know, there will be two phases present, there will be solid and there will be liquid present. So what is the percentage of solid, that means in volumes, what is the fraction of liquid and solid? That will be uh, explained by liver rule. So how? So as the name suggests, they just take these to be a lever. Okay, so this point is my P and this is my Q, and somewhere here I have my 50 percentage, this is 40 and this is 60. Okay, now it tells us that if you want to calculate the fraction of liquid, okay, anything in rather, but here in our case if we want to calculate the fraction of liquid, it just tells that to take the opposite lever, okay, on the numerator. So for example, the fraction of liquid is what I want. Simply I'm writing FL. So it is asking, if I mark this as R, it is just asking to take the opposite lever, that is RQ, the length of the opposite lever, divided by the total length of the lever, that is PQ, RQ by PQ, of course, into 100 for percentage. Similarly, for fraction of solid, what it gives us is again the same thing, taking the opposite lever, that is PR, divided by the total stuff PQ into 100, right? So this is what you do for the fractions. How much is the fractions? So in my case, the fraction will be nothing but 60 minus 50, it will be the length, divided by 60 minus 40. And yeah, the same thing here, when you apply, it will be 50 minus 40 divided by 60 minus 40. Okay, so in my case it's 50 percentage. Okay, so this is how you calculate both the stuff, the composition of liquid and solid, and also the fraction, how much is the percentage of my stuff present in it. Okay, so from these two, using different equations and all, you can also calculate different alloy temperatures. Okay, so you can see here, for example, the same 50% alloy, if we consider, you are having a range of solidification over here. Okay, so this tells us about an interesting part, that is the cooling curve. Okay, so I'm drawing it here itself. So if you take the cooling curve, what is a cooling curve? It just tells us the temperature versus time. Okay, temperature versus time. So this gives us the cooling curves and also the rates, cooling rates. Okay, so until it is coming to the temperature of just a minute. Yeah, so it is, if we start from here, the temperature is decreasing, it reached the liquidus. From here also it has a particular range of temperature, something like this, and from here it goes somewhere like this. So if you see here, it has some range over here, TT is there, that is what is denoted by this. Okay, if you take a normal curve, for example, if you, this is the curve for this case. Okay, if you take the pure metal, how it will be there? So you know, for a pure element, the melting point or is a constant, boiling point is a constant. So this is the cooling curve, where you are not seeing any delta T over here. Okay, it is a constant. These are usually called in isothermal curves. Okay, so by telling this, the same cooling curves can be also observed in some other type of phase diagrams, okay, or some other type of microstructures. So those are nothing but the eutectic. So this is one more uh, kind of binary phase diagram where you can find the cooling curve which I was mentioning. Okay, and how this will be done. So usually we know, oh, someone is waiting here. Admit. Yeah. So This eutectic phase diagram, we know the solid solubility, okay, or formation of the solid solutions, okay. The solid solutions formation require many rules, right, according to the Hume-Rothery rules, okay. So we have many rules that should be satisfying in order to have complete solubility or the extent of solid solution formation, okay. So what can we do, or rather in practical cases we don't find 100% solid solubilities, okay. So we are not finding this. So what if the case, how will be the phase diagram change, okay, if there is no complete solubility, okay. Then the phase diagram looks something like this, okay, where we have, this is how, so again some percentage of B temperature, okay. This is how my phase diagram look like, okay. Again, as I said, everything, every curve has some important description, okay. So by forming some lens types we intersect it, and then by cutting it we get this, which we'll be discussing in our maybe course, okay. So if you see here, the same thing, we'll try to plot it. This is a liquid, and these are the solid solutions which we have over here. This is one solid solution and this is the other solid solution. So the first one, let's call it alpha, and the other one beta, okay, maybe. And this is the intersection between this, that's alpha plus beta. And now what we have here, this is L plus alpha and this is L plus beta. We have this now, okay. So this is eutectic temperature, eutectic phase diagram. So if you see, you can use everything in whatever we have discussed, like phase rule, tie line, lever rule, everything is applicable here. But the reaction over here, this, the reaction at this point is the new thing, because there, if you see, my liquid is transitioning into two solids. This is the eutectic reaction, and this temperature is called as my eutectic temperature, okay. So this is eutectic reaction, okay, where my liquid is directly coming into solid. So just now, as I said, something is coming like this, okay, where the cooling curve is temperature and time again, which has an isothermal curve where the temperature is not varying. It is not having a range of temperature, but it is having a constant transformation temperature, okay. That's what I wanted to tell. Now here also there are some classifications which I wanted to explain. So where, if we take less than the percentage of eutectic, maybe this is the percentage of eutectic, okay. And if we go less than that, we call hypoeutectic alloys, and if we go more than that, we call it hypereutectic alloys, okay. So this is what are the two categories. And here what is happening here is that, so if you observe, the regions are changing as we just change the composition by small amounts, maybe less or maybe more. My liquid, okay, whatever is there, it is not liquid anymore. If you observe in the diagram, if you come into hypo, it is L plus alpha. Similarly, if you go beyond that, it is L plus beta. The liquid is only at that particular point of time, that particular composition, okay. So this is an important thing that to be noted now. And there are many characteristics of eutectic. So eutectic can easily be identified in a microstructure by, because it is having a lamellar structure. So what is a lamellar structure? So this is my some grain, uh, alternative layers of alpha and beta can be found, something like this. These are the three grains if you can see. And alternatively, so if my blue is beta, this is beta alpha, okay. This is something you must know easily. Fine. Now, one more thing that you must also notice is what will happen. Just a minute. Yeah, what will happen to my structure if I'm not having liquid totally? For example, we can completely identify eutectic if we have liquid transforming into the two cases, two solids. But what if I have these two cases? We have also that, so we have to also consider that. So what we can do is that if you are having this, okay, as your initial content, this will be forming into this only, but this alpha will be of two parts. One is the pro-eutectic, which will be seeing it what it is, and the other is eutectic. Okay, now what is this pro-eutectic? This is a new word. Okay, so if you can see here, our eutectic reaction, what is the eutectic reaction? My liquid is transforming into alpha and beta. So but what are the reactions, what are the reactants that I have along with my liquid, I have one more alpha that is present with me. So that indicates that this liquid will be forming alpha plus beta, plus this alpha from my initial reactant will try to grow and form a pro-eutectic alpha. So that's what how we write. So this is a pro-eutectic, and this is the usually how the eutectic reaction takes place and it forms. Now this is the difference between this. So the alpha, not only alpha, if you see on the hyper side, it will be pro-eutectic beta, right? So if you see at this alpha, so that alpha, whatever is present, it is forming my pro-eutectic alpha, and my liquid is forming alpha plus beta. Now the thing is, how can we notice? So if I'm having my matrix of eutectic, okay, so otherwise I'll just draw it here again. So these are my lamellar structures. Okay, my eutectic, pro-eutectic alpha, for example, if I'm taking pro-eutectic alpha, how will this be? So these will be present inside this matrix, something like this. The chunks of pro-eutectic alpha can be found inside the matrix of eutectic. Okay, so this is this, and the rest is my eutectic matrix. Okay, eutectic matrix. Now this is how you can easily identify in the structure. Now again, how to apply, how to calculate this? So I'm just drawing the same image here. Okay, so I just drew the same thing. Now what I wanted to see is that how much is my pro-eutectic alpha. Okay, how much is my pro-eutectic alpha? So if you see here, when will my eutectic reaction take place and when will my pro-eutectic take place? Okay, so the pro-eutectic take place if you are in this region. I'm using different color in this region, right? So whatever alpha is present in just above, actually to differentiate I drew it above, but you must take the temperature just above the eutectic point, eutectic temperature. Okay, and similarly you must draw just below the eutectic point. So these are the two cases. Why we consider this? So the first thing is just above the eutectic, the last alpha that is present, and that means whatever alpha that is present, that will be my pro-eutectic. So just above the temperature T, I'm just mentioning T as the eutectic temperature. And if you see that and calculate by applying my lever rule. Okay, for some other, if I am calculating for this alloy percentage p, fine. If I want to calculate for this alloy, and if you are looking at it, how much is the pro-eutectic alpha, what you must do is just label it, we're taking it some pqr again, and my pro-eutectic alpha will be according to the lever rule. I guess everyone should be able to do this. That will be my rq divided by pq. This will be by pro-eutectic alpha, right? Now, along with this, what will the total eutectic? So, for calculating the total eutectic alpha, for this purpose, we came just below the eutectic temperature, because just below the eutectic temperature, we know that the whole transformation is completed and we are in my solid zone. Okay, so in my total solid, how much is the percentage of alpha present? That is what, if we can calculate, we can just subtract this and we can calculate what is the amount of eutectic alpha that is formed from the reaction or from the transformation. So how will be calculating this? So just take some x, y, and z. So if you want total alpha, and yeah, this is alpha and this is beta, of course, as I mentioned. So this total eutectic alpha will be equal to zy divided by xy. Okay, so this will be my total eutectic alpha. And again, as I already shown in the previous slide, that my total alpha will be coming from two different sources. One is the eutectic from the transformation, and the other is the pro-eutectic alpha. Okay, yeah, I'm considering a hypo-eutectic steel or whatever alloy, so that's why I mentioned alpha. If it's hyper, then you have to calculate pro-eutectic beta. Of course, you know that this will be L plus beta and L plus alpha. So from there, you'll be getting the pro-eutectic alpha or pro-eutectic beta. Okay, so we, from this, whatever we calculated, we know this and we know this. So if someone asked you to calculate your eutectic alpha, it's just that easy. Subtract total minus pro-eutectic. Just simple that you will be getting your eutectic alpha calculated for you. Okay, so this is how you calculate in your uh, values. Okay, the percentages using lever rule, and the other one is the tie line. Obviously here what I did is I drew the tie lines at different temperatures, right? Different temperature in the sense just above and just below. That's what I did. Okay, now we saw these two. Similarly, we have many more reactions. Okay, we have eutectoid, we have peritectic, peritectoid, monotectoid. These are all the reactions that are uh, possible. Okay, so now what we can look at is how the reactions will be there. Okay, so as I already said, the microstructural differences can easily be known. The one thing that you must know, how the reactions and their what you can say, identities inside my phase diagram. So by looking at it, you can easily know, okay, this is something looking like my eutectic alloy, eutectic reaction. Okay, so how we can do it? So I'll just explain you. So I think we already discussed the eutectic. Okay, so if I can just draw like this. Okay, so oh, my bad, it's not straight at all. Just a minute. Okay, so I got this. Someone is talking. I'll just mute them. Yeah, I muted. Now, so for eutectic, what will be the reaction? So the reaction will be liquid forming or transforming into two different alloys. right? So liquid will transform into two different colors, that is alpha plus beta. Transforming in the sense, that's nothing but cooling. We are coming from higher temperature to a lower temperature. That's what it is. Okay, so the liquid, usually, one more thing you must know is everything that is mentioned in our phase diagram are equilibrium. Okay, that comes the point which I want to discuss in the next topic. But you must know the phase diagrams are all equilibrium diagrams. Okay, so obviously you will be having some differences, okay, when some metastable phases are forming, but usually the equilibrium diagram is as it is. I mean, equilibrium diagram is what they call the phase diagram. Okay, so that's why I introduced this equilibrium symbol. Now, how will this look like? So you already just now you saw it. This will be liquid, this will be some alpha and beta, and this will be alpha plus beta, the reaction. Okay, so this is how. Okay, if you can see that my liquid is on the top and the phase diagram is something like this, okay, then you must be telling that this is a eutectic reaction that is taking place. Okay, similarly, as I said, the other reaction, so I'll just write down the reactions for you. Eutectoid, peritectic, peritectoid, and we also have monotectic. Okay, and one more is synthetic. So these are the different reactions actually that are present. So if you see at them, eutectoid is nothing but when one solid is transforming into two other solids. Okay, now how will this be like? Okay, so this will look like the same thing, but on the top will be something like this. Okay, the top region is changing now. Instead of liquid, it is now other solid gamma. Okay, similarly, peritectic. So peritectic, I think all these reactions are, if you already studied iron carbon diagram, you must be familiar that many of these reactions will be present in the uh, reactions. Okay, so now the next reaction is peritectic, that will be L plus alpha gives rise to beta. Okay, that means two different things are coming to form one, so that will be like this. In our case, so this will be peritectic, right? Oh, oops, as I said. Okay, so this will be my peritectic, where L plus alpha will be on the other side and beta on the other. Yeah, obviously you can just write it top or bottom. Okay, but the thing is, you must observe is the reactants and the products. How are my reactants and the products? Similarly, peritectoid is nothing but just replacing liquid by solid again from the eutectic, from the peritectic. Okay, so what we did here, from liquid we changed to another solid. Same thing if we do here, it will be this thing. Okay, so this will be something like this, gamma plus alpha, this will be beta. Okay, similarly the other two are monotectic. So monotectic is forming a new liquid and a new solid from the existing liquid. Similarly, if otherwise I can just mark this. Synthetic is an equilibrium between two liquids and one solid alpha. Okay, so as I said, you can just do this, right? Mm, okay, so these are the reactions that are usually possible. Okay, and now, as I said, as I just now discussed about this, what will be my equilibrium? I mean, as I said, phase diagrams are called as equilibrium diagrams. So what is the governing factor? So any equilibrium, the governing factor or the driving force is the Gibbs free energy. That's delta G. Okay, you must be knowing by now. So how the delta G is affecting my compositions or the equilibrium, right? Equilibrium is linked with my composition. So usually we draw G versus X curves. Okay, G versus X curves we call. The derivations and all we'll be discussing in the course detailedly. But now just wanted to discuss for these two, like whatever isomorphous I have told you, and also for eutectic. Okay, so how the governing factor of Gibbs free energy changes. So firstly, I'll just draw this. This is my isomorphous diagram, which I already discussed just now. Okay, and always remember, always and always, these Gibbs free energy versus X curves will be drawn for a certain temperature. Okay, at a particular temperature, how my Gibbs free energy is varying with my concentrations. Okay, and I'll just take three different regions and I'll show how they will be changing. And I said curves because these will be like cup shaped curves. Okay, so this is G, this is my X, these will be cup shaped. Okay, so why, how we got this curves, everything as I said we'll be discussing in the course. Okay, so now we have three different regions, right? So we have liquid, we have solid, and we have LPSS. So I want to draw the G versus X curves in these three diagrams. Okay, so I'll just take a temperature here, I'll just take other color, this one, and this one, T1, T2, T3. So at these three, so why I took this, because they are having three different regions, right? We have liquid completely, we have solid completely, and we also have two different phases. So at T1, how will be the curve? Okay, so I think you have already should be knowing that anything that is having lower Gibbs free energy is spontaneous or is stable, okay, at that particular temperature. So what is stable at my temperature T1? That is my liquid L. Okay, so the curve should be at the bottom and my solid should be on the top. This is what will be at T1. Okay, so if you can draw this GS, and this is GL. Okay, so this is how the G versus X curves will be there. Don't worry if this is not clear. Definitely in our course we are going to detailedly discuss the derivations of all these and also how we got arrived with this. Okay, now one more thing, at the other temperature, right, at T2. So this is interesting. So here we have two different phases. So what can be done is that this is my thing. I'm using orange for liquid and green for, I mean green or blue for solid, so that it makes us uh, to observe the differences clearly, right? So now I'm drawing my liquid. So initially in this range, if you see the phase diagram, okay, in this range, which one is stable? My liquid is stable in that reaction. Similarly, if you come into this region 2, that is in the two phase region, both are present, and after that, after this particular composition, this thing is stable, that is solid. Okay, that means, so these points are also important for us. Whatever these 4 points can be plotted, so I'm just plotting that as X, Y, uh, Z, and some W. Okay, X, Y, Z, W. Okay, now how can we do it? So as I said, liquid, so my liquid is stable, so it goes like this. Now from here, from this temperature, my, so this is my GS and this is my GL. Okay, so there should be, I mean obviously there is some, if there is some equilibrium and we are talking about an equilibrium, we can easily draw a common tangent. Remember, this is a golden tip for G versus X curves, where if you are drawing a common tangent between two curves, that means that the compositions at the intersections for the common tangent gives us the compositions at the equilibrium. That means in my case, if I Okay, I think you are not able to see. If it is not clear, I have just zoomed it. Okay, so this is the common tangent. Okay, now you can see the difference clearly, right? This is the equilibrium point of one solid, and we have the other one. Okay, now what does it mention? So remember that common tangent gives us the equilibrium. Why and how, as I said, we'll be discussing later on. So this gives us the composition of liquid, some Cl, and this gives us composition of solid, which is in equilibrium. Okay, these two are nothing but again the same things which are on my Tyler. So as I already named them, I'll just do the same again. So this is my X, this is my Y, this is my Z, and this is my W. Okay, this is how the stability can be seen. Okay, so again you can divide it into the regions. So we have got three regions, right? Yeah, so we have got three regions in our phase diagram, right? You can observe this. So this is the first one, this is the second, and this is the third. Okay, so the same thing, first, second, and third. Okay, so if you observe, what is the stable phase in the first one? That is my liquid. So here, if you can observe here, my liquid is on the bottom. That means that my liquid is having the minimum Gibbs energy. Similarly, in this region, both the liquid and solid, both the liquid and solid are in equilibrium. So you can observe both are there, both has a minimum. This, okay, depends again on the fractions, compositions, and all. Which one is dominant? That means which phase is present to more extent. Okay. Similarly, the third one, which is the phase that is stable, that is solid. So here you can see my solid is on the lower side. That means my G versus X curves are explaining me the stabilities, and also you are directly calculating your compositions because the x-axis is composition, right? So from the phase diagram we can do this, or rather from experimental data we form G versus X curves, and by doing this at a range of temperatures we conclude the phase diagrams. Okay, from G versus X curves, in this particular temperature we got these two, in some other temperature we'll be getting some other, and by taking the locus of all these points we will get our isomorphous phase diagram. Okay, that is how we are concluded with from the G versus X curves. So similarly, I think we can also do this from, for I think you can now do, I guess the concept is clear for everyone. So what we'll be doing is we'll be doing at T3. Okay, so at T3, which one is stable? At T3 only solid. So it's very simple, right? We can just take this. Somewhere here will be my solid and this will be my liquid. There is no intersection at all. GS and this is GL. Fine. So now you can see how we got the points, different points, and from there we have concluded with my phase diagrams. This is only for isomorphous. You can do this with any other eutectic, any other important alloy. You can do the same, and you can come up with, or generation of phase diagrams, or rather they call construction of phase diagrams, can be done for any new alloy that you can generate. Okay, so this is for my isomorphous diagram. Similarly, you can also do for eutectic. So quickly we'll do the same, and okay, we'll wrap this session up. So this is my Eutectic diagram. Now again I'm taking the three regions over here. One is just above, one is here, and one is here. So this is interesting. The number of phases are more. This is liquid, liquid plus alpha, liquid plus beta, alpha plus beta, alpha, beta. Okay. Now at T1 it is easy. Only liquid is This is at T1, only liquid is the dominant one for you. Okay, so what you will do, you can simply draw that. Okay, so the next important thing is T2. I think T1 can be easy for you. I'll just draw it. You'll be having your liquid here, alpha and beta somewhere on the top. Okay, so this will be your Gl, G alpha, G beta. Fine. So my liquid is stable throughout the composition ranges. So I hope you will be able to do it. Now we'll discuss T2. Okay, I hope this is interesting because there are many points, so we'll point it out. So this time I'll do it 1 2 3 4 5 6 points. So if you can see, we have to get 6 points on my G versus X curve also. Okay, so again we'll see the which phase is dominant. So in this alpha, this is liquid plus alpha, this is liquid, this is liquid plus beta, and this is my beta. Okay, now how I'll draw it. So this is my alpha, this is no, otherwise I'll just do it. This is my, I'll just move it to the bottom a little bit. This is my liquid, and one more stuff that I'm left with is my beta. This white is beta and this is alpha. So here now I'll just draw the common tangents, so that we can know the intersection points. Okay, as I said, these are the inverted C curves or the cup shaped curves for G versus X. So I'll just draw the common tangents now. Okay, so this thing, oh, this thing, oh no, yeah, this thing, yeah, these are the two common tangents that we have, right? So what we are bothered is to see how we are getting the points. So obviously this will be 1 until here. If you see, this is until here. I think everybody is able to make up. This will be the alpha is stable, that will be 2. Okay, until here, this is my common tangent meeting my liquid, and this is my common tangent of beta meeting the liquid. See the part now. So we have got 3 point, 4 point, and this is the 5, and obviously where it goes and hits the beta, it will be 6. So interesting, right? We got all the 6 points. What all the 6 we have discussed here, we got everything. The same stuff we can write here also. This will be alpha, this will be alpha plus beta, sorry, alpha, alpha plus liquid, liquid. Here if you draw one, this will be, sorry, this will be beta plus liquid. Finally, this will be beta, right? So it's interesting. We got everything over here. Alpha, alpha plus beta, alpha plus liquid plus alpha, liquid, liquid plus beta, beta. Everything we got when we are changing the Gibbs free energy versus X curve. I mean, if we are drawing a T2, right? So this is an interesting stuff. So that thermodynamical stability can be known for any phase diagram using this. Okay. So one more thing we are left with is T3. Add T3. Okay, so if you see here, we got 1 2 3 4, only 4. So there is no liquid at all. So the curve will be, this is my alpha, this is my beta, and my liquid will be somewhere here. So what it is showing, as this equilibrium curve is having a very high energy, right? Here if you see, this is delta G, the point on the liquid is having very high energy. So what it is does, what this will do, it will just take another friend here, that is beta, and form equilibrium with it to form one common tangent. So this is having higher energy, so it is not, similarly the same case is with this. It's not forming that, instead it is taking a more spontaneous path, or you can say more stability. Obviously any atom will choose towards the stability path. So what it does, it is having your 4 points, and these are alpha, alpha plus beta, because the equilibrium is between alpha and beta now. There is no liquid part. Okay, so this is beta. This is what your temperature 3, the curve at temperature 3 will look like. fine. So yeah, pretty much covered what I wanted to convey you guys.